Hello everyone. Thank you for attending the BAS Electrochemical Webinar 2021 August. I'm Miho from International Sales Team, and I will be the moderator. Before we start, as unusual, we will ask you to don't be worried to record and enjoy the webinar. We are recording, and we will send the direction to you as soon as it's ready. In this way, you will be able to review the full webinar. Also, if you have any question, please feel free to contact us. Well, let's start today's webinar. The first part will be introduced by Professor Noriyuki Watanabe, a former assistant professor of the Faculty of Engineering at the University of Tokyo and BAS Technical Advisor. The theme is Cyclic Voltammetry Basics.
It's the basics. This is a very fundamental area of electrochemistry. Cyclic voltammetry, abbreviated as CV, the most popular and fundamental method in electrochemistry. It's a potential scan and sometimes repeated potential scanning, and then recording current change. Information obtained these methods are like this. It's intuitive, qualitative, quantitative. Redox potential is thermodynamics parameter, and reversibility, chemical, electrochemical kinetics. This is another important area of physical chemistry, kinetics. And we can obtain the chemical reaction mechanism by this method. As usual, ferrocene as a typical sample. CV obtained for ferrocene, showing reversible fast electron transfer. Ferrocene is a typical metal organics, cyclopentagienyl moiety, sandwich ferrous ion. This schematic here. Divalent iron is sandwiched cyclopentagienyl ring. This cyclopentagienyl 5-carbon ring. This and hydrogen is bonded 5 hydrogen. This molecule, ferrocene, is symmetric small peak to peak CV is obtained by this molecule, like this. The schematic representation by CV, this positive potential. This direction is negative potential. So the ferrocene is oxidized this direction and reduced. Oxidation peak is this, and reduction peak is this. Ferrocene, usually ferrocene is a neutral compound. This moiety has -1 charge, and this another 1 charge. So ferrous ion is main parameter in cyclic voltammetry. This typical CV profile. This direction is minus potential. This is a plus. So this is oxidation peak, and this is a reduction peak. C means cathodic. E0 is redox potential. EPC is reduction, and EPA oxidation peak potential. These reduction and oxidation peak current respectively. Delta E means peak potential difference. The difference between EPC and EPA. IPC-IPA means peak current ratio. IPC reduction peak and oxidation anodic peak, cathodic peak. ratio is peak current ratio. Above all, apparently recognizable. This we recognize each parameter. U or V means potential scan rate. Apparently unrecognizable parameters are also important. Electron transfer parameter. And alpha is a parameter, transfer coefficient. And in KE, small kf or small kb are necessary for following internal chemical reaction. Main important equations. Peak current is the fast electron transfer and diffusion controlled case. This peak current for fast electron transfer. In this case, the diffusion controlled case. Peak current proportional to root of scan rate V. It is not necessary. We need not to remember these parameters. Just we know about V, scan rate, And A means electron surface area. C is concentration of solute. D diffusion coefficient of solute. V potential scan rate. N transfer electron number. This important point is peak current is proportional root of scan rate. Peak current in the case of adsorption. In this case, it's different from non-adsorption case. IP proportional to scan rate directly. You have to remember the difference between diffusion case and adsorption case. For adsorption case, the IP is proportional to V scan rate directly, not root V. Notice the difference in dependence of potential scan rate V for diffusion or adsorbed species. This is an important point. It's very useful to understand the CV profile. IP is proportional to root of V for diffusional case. Apparently unrecognizable parameter, electron transfer rate, Ks. We cannot know about Ks suddenly. Or transfer coefficient alpha is not also recognizable. Also, diffusion constant D. This parameter is important, but not recognizable directly. Additional important parameters is uncompensated solution resistance, RU, or double layer capacitance, CDL. These parameters we can not recognize suddenly from CV. Just we estimate the uncertain value. It is interesting how these parameters affect the appearance of CV profile. Dependence upon electron transfer rate Ks from Ks equal 0.1 centimeter per second. This rather fast electron transfer. And ferrocene, in case of fluorescent, this value Ks is extremely large, very fast transfer. This point, from this point, the ferrocene is a very important material. This point 0.1, the Ks is below, and peak potential different widen this like this. Further decrease of Ks, the peak-to-peak difference become very large. From the profile, we can roughly estimate the Ks value. This K point 1, this, and point 0.01, and then point 0.001. The smaller Ks, the big difference. The decrease of electron transfer rate Ks result in an increase of peak-to-peak difference of CV. These are important point, the information obtained from CV measurement. This CV profile is example from these parameters. Alpha transfer coefficient is constant. And also, diffusion coefficient is constant. This value 10 minus 5 fifths is rather very fast diffusion. This value of diffusion coefficient constant depends on the molecular size. A small molecule is fastly diffused. And the Ks is this very small electron transfer. In this case, the peak-to-peak difference is very large. These are very small. Roughly, we from this value is fast electron transfer. This medium. This value is rather slow electron transfer. Effect of transfer coefficient alpha is a very difficult parameter to understand. In this case, point 0.01 is rather fast electron transfers as a category. This and following figure is dependence on alpha. Alpha rather large case, the reduction peak is larger. And this the reverse case, the alpha is 0.2. It's a very small value, and in this case, oxidation peak is exaggerated. This alpha value of alpha is between 1 and 0. So this usual case alpha is 0.5, and it is very difficult to understand how this value is obtained. We just effect of diffusion coefficient. Diffusion coefficient is has a large effect. This value is very small. Small moiety like hydrogen or proton is approximate to this value. And larger molecule is this value getting smaller or larger molecule. In this case, K is as Ks 0.01 and alpha 0.5. This a typical case, and the profile rather seems very different. So we understand how value of diffusion constant affect CV profile. Diffusion coefficient depends on the size of a molecule and its electric charge. the relation between electron transfer rate Ks and potential scan rate. This is another important point in the case of we understand the CV. Peak current is proportional to scan rate. This profile shows dependence of scan rate dependence. The potential scan rate is for small Ks, the very slow electron transfer. The peak potential difference is increase with scan rate. This potential scan. This very slow scan rate, and then so you can understand by varying potential scan rate. The, you can roughly estimate the electron transfer rate. Estimation of electron transfer mechanism. Simple E, moiety A reduced to B. EC mechanism is a chemical reaction in solution occurs. B called convert to compound C, or ECE is another. Then C is electrochemically react. In this case, C reduced to D. CV profile depends on each mechanism. Possible to estimation of the mechanism from CV profile. Mechanism E, A reduced to B, etero redox point, electrochemical reversible, alpha red point 5, Ru uncompensated resistance 100 ohm. Electrode area. This is the simulation profile for this parameter. CDL is a double layer capacitance about this. This parameter reflect on this difference from ground level. CDL, larger CDL, the difference become bigger. This is rather fast diffusion case. One electron reduction current is given as next current. Diffusional current is proportional concentration gradient at electrode surface. X0 means electrode surface, and proportional to diffusion constant. Electrochemical current, diffusion current is like this. Current is proportional to both concentration gradient and diffusion coefficient of the solute at the electrode surface. You remember that both electrode surface is important point. This CV profile and this translation profile around electrode boundary. Here is positive electrode surface. The solution distance from distance from electrode surface. Then this potential is beyond the peak potential. This still gradient surface concentration increasing. Now then decrease the gradient concentration gradient electron boundary gradually decrease. profile line extend to this direction. This now this this concentration gradient gradually decrease, and this concentration profile reversed. This final stage of this important point is this concentration profile initial molecule and product profile of this product maximum concentration of product close to electrode. It is visible to image of concentration profile of product and initial product molecule is important. I recommend you memorize this discussion. About the mechanism EC, a product of electrochemistry is C. Concentration profile of solid changes depending on potential. B changes to product C. These are chemical reaction in internal solution. And this parameter, chemical parameter of chemical reaction, equilibrium constant and reaction rate Kf. In this case, the potential concentration profile of electrode boundary cross solution. Attention why this profile is shown is I recommend to imagine concentration profile in cross solution. It is an important point. This case of EC, electrochemical and chemical reaction is followed. In the case of presence of after reaction of reduced product, this reaction equilibrium constant and Kf is rate. This Kf 0, there is no change, and then the case of Kf 0.1, this, and for 0.5. And the 10, so EC, the case of EC reaction, equilibrium chemical reaction give a very different CV profile depending upon value of Kf. Caution related solution resistance. This concept is very important for primary stage student. Difficult to understand the importance of this concept. This counter electrode, working electrode, and R is a reference electrode. And potential stat cannot control exactly potential control to working electrode if flow. This potential stat controls the difference of point position of reference electrode. This potential difference cannot be recognized by potential stat. So current flow make potential drop proportional to current times solution resistance. This current, so this potential difference deficit due to uncompensated resistance applied potential by potential stat. We cannot exactly we cannot recognize potential distribution in current flow. this potential difference. Solution resistance between working and reference electrode cannot be compensated by potential stat. This is a weak point potential stat have. So this potential difference is deficit in expected amount in potential. Additional peak-to-peak difference caused by uncompensated solution resistance. This simulation figure. The peak difference increase with increasing compensatory resistance. How to be reduced? Let electrochemical current or RU smaller value by decrease solute content or use smaller electrode. This is a simulation by small electrode. Just making sure. This is another extra caution. KS is 0.1. This is fast electron transfer and RU, uncompensated resistance, R or black. This real resistance between working and reference electrode. And red line or 10 times larger. Others same as peak shift larger for reduction. This reduction direction. So the base pointer, this reflect this increase. So this potential difference is real current magnitude. So there is a minor difference. Case is 0.1. This fast electron transfer and this small uncompensated resistance and this 10 times. There is a certain small difference in potential shift. This small potential due to different absolute value of oxidation reduction peak current. Absolute value means this and this direction is this background current and this. So this difference has influence about this magnitude. Absolute value of peak reduction current is larger, and so its peak potential shift is larger. This side is larger than this. This is an important point. Precaution, just electron transfer rate and uncompensated resistance reflect similar effect on CV peak potential difference. For example, this increase 10 times larger and same electron transfer rate. This KU are this 10 times. So it's better to use very small resistance and a small resistance. Another point is double layer capacitance. Double layer capacitance is Helmholtz array and diffusion array. This TL is in general CD THC Helmholtz array capacitance. So CDL is approximately CH. The reaction among capacity, electric charge, and voltage, the Q, this general principle. Difference it by time. C, and the dq equal current. Time difference, differentiation of charge equal electric current. time differentiation of electric potential equal potential scan rate. Multiplication of potential scan rate and capacity equal electric current. Background current flow always proportional to capacity. We cannot escape the influence from capacity. Capacitive current. It in many cases give struggle. This final slide summary. CV is the most popular and general method. If you understand the content today mentioned and master that, you will obtain a lot of result. Good luck. That's all today's lecture.
Thank you, Professor Watanabe. The second part will be presented by me. Well, this video introduces some basic concepts about electrochemistry for researchers who are studying electrochemistry. The first part of this series will introduce the following topics. Electrochemistry is the science that studies the interconversion relationship between electrical energy and chemical energy. It belongs to the field of physical chemistry research. The fundament of electrochemistry is the interconversion of electrical energy and chemical energy through redox reactions. The object is the study of the phenomenon of charge interface formed by two types of conductors and the charges that occur on them. The application of electrochemistry is very wide, and it is no exaggeration to say that it is closely related to our daily life. The progress of an electrochemical reaction, like any other chemical reactions, follow chemical thermodynamics and chemical kinetics. Here is a brief explanation of chemical thermodynamics and chemical kinetics. Chemical thermodynamics is a subdiscipline of physical chemistry and thermodynamics. It is the study of the energy changes that accompany the physical and chemical changes of this material system under various conditions, so as to make accurate judgments about the direction and extent of chemical reactions. Chemical kinetics, also known as chemical kinetics and chemical reaction kinetics, is the study of the rates and mechanisms of chemical process. It's a field of physical chemistry that studies the rate of chemical process and the mechanism of the reactions. Next, let's look at the redox reaction, which is the fundamental of electrochemical reactions. A chemical reaction that involves the gain and loss of electron is called a redox reaction. The reaction in which a substance loses electron is called an oxidation reaction, and the substance that loses electron in this reaction is a reducing agent or reductant. Conversely, the reaction in which a substance gains electron is called a reduction reaction, and the substance that gains electron in this reaction is an oxidizing agent. The chemical reaction of carbon combustion with oxygen is one of the simplest redox reactions. In these reactions, carbon element loses electron. An oxidation reactions occur, and the carbon molecule becomes a reducing agent. At the same time, oxygen element gains electrons. A reduction reactions occur, and the oxygen molecule becomes an oxidizing agent. Combustion is the most intense redox reactions, where chemical energy is converted to the thermal and light energy. The number of electrons gained by the oxidizing agent is equal to the number of electrons lost by the reducing agent. Next, let's look at the slow redox reactions. For example, the corrosion of metallic iron. The figure on the left shows a simple iron plate corrosion experiment, where iron plate is immersed in water containing dissolved oxygen. It's well known that the iron plate rusts after a period of time. This reaction is similar to the phenomenon that normal iron products are exposed in air and water, and corrosion occurs naturally. The reaction at this time is at this equation. This is a reaction in which iron is oxidized while oxygen is reduced, and the entire iron is converted to the iron hydroxide. These reactions can theoretically be divided into two half reactions. Iron atom loses electron and becomes iron ion. At the same time, oxygen gains electrons and becomes a hydroxide ion. Since electrons will not be generated from nothing and will not disappear from nothing, when performing redox chemical reactions, there must be a part that supplies electron and a part of accept electron. The oxidation half reactions and the reduction half reaction must occur in pairs at the same time and are inseparable. Here, is there any way to distinguish the oxidation half reaction from the reduction half reaction and proceed independently? The answer is yes. It is an electrochemical redox reaction. Electrochemical redox reactions is a reaction in which electrons are gained or lost at the electrolyte interface of the solution through the potential difference between the two electrodes or through the use of an external power source to make a potential difference between the two electrodes. Electrochemical redox reactions are characterized by: in electrochemical measurement, oxidation and reduction reactions are carried out separate on two electrodes, and one of the half reactions can be observed in detail. By varying the potential of the electrodes replace the oxidizing and reducing agents needed for the chemical redox reactions, and the direction of the redox reactions can be controlled. It can be said that any redox reactions can be realized electrochemically using electrodes. It be considered that the protagonist in an electrochemical redox reactions is the electron. In order to first understand electrochemical redox reactions, it's necessary to first understand the primary cell and electrolytic cell. A primary cell, or primary battery, is a device that converts chemical energy directly into electrical energy through a redox reaction. This type of cell is the dry battery we use in our daily life. Here is a schematic of typical primary cell, the Daniell battery, the zinc-copper primary cell. The zinc electrode is immersed in the zinc sulfate solution on the left, and the copper electrode is immersed in the copper sulfate solution on the right. The two solutions are connected by salt D. When the external circuit is connected, it can be seen that the zinc metal electrode gradually dissolves. The zinc is oxidized and loses 2 electrons and becomes a zinc ion, which enters the solution. And at the same time, the copper electrode immersed in the solution of the copper ion gets electrons to reduce the reaction, resulting in a copper metal which is deposited on the electrode. The negative electrode of the cell undergoes oxidation reactions, which lose of electrons, and the positive electron of the cell undergoes a reduction reaction, which gains electrons. Therefore, by using an electrochemical device such as a primary cell, the oxidation and reduction reactions can be distinguished between the two electrodes. In general, the following basic conditions need to be met to form a primary cell. Two metals with different activity are connected by wires and immersed into the electrolyte solution. Current is generated due to the oxidation and the reduction reaction. at the two electrodes. In a primary cell, the highly reactive metal is the anode, and the less reactive metal is the cathode. The anode itself easily loses electrons in the oxidation reactions, and the electrons flow along the wire to the cathode, where they are converted into electrons. In general, the cations and the electrolyte solutions will gain electrons in a reduction reaction. In a primary battery, the external circuit is electrically conductive, and the electrolyte solution is ion conductive. The positive and negative electrons of primary cell are determined by the properties of the electrode material itself. It is a spontaneous redox reaction. Next, let's take a look at the electrolytic cell. Contrary of the primary cell, an electrolytic cell is a device that converts electrical energy directly into chemical energy. By controlling the potential and current on the electrode via an external power source, a potential difference is generated between the two electrodes in the electrolyte solution, and the process of oxidation reduction reaction is called electrolysis. Here a schematic of the simplest electrolytic cell. Two carbon rods are immersed into the copper chloride solution, and the carbon rod on the left side is connected to the positive pole of the external power source to become the anode of the electrolytic cell, and the carbon rod on the right is connected to the negative pole of the external power source and become the cathode of the electrolytic cell. When the external power source is turned on, an oxidation reactions occur on the left carbon rod electrode, causing the chloride ion to lose electrons and become chloride gas, making this carbon rod electrode the anode of the electrolytic cell. At the same time, a reduction reactions occur on the right carbon rod electrode, and the copper ion gains electrons to become metallic copper, which is deposited on the right carbon rod. This carbon rod electrode is the cathode of the electrolytic cell. The following basic conditions must be satisfied for the configuration of the electrolytic cell, where the electrolytic reaction takes place, and the characteristics of electrolyte cell. Next, let's compare the primary cell and electrolytic cell. In a primary cell, oxidation occurs at the negative electrode and reduction at the positive electrode, and spontaneous oxidation reduction reactions occur through the difference in electrode potential between the two electrode materials. In an electrolytic cell, a reductions occur at the cathode and an oxidation reactions at the anode, and a non-spontaneous oxidation reduction reactions is forced at each electrode by using an external power source. In terms of energy conversion, a primary cell converts chemical energy into electrical energy, and an electrolytic cell converts electrical energy into chemical energy. So, why can a primary cell react spontaneously? A primary cell contains two electrodes. When the external circuit is interrupted, the potential difference between the two electrodes becomes the electromotive force of the primary cell. The magnitude of the electromotive force is determined by the nature and condition of the reactions taking place in the cell, for example, concentration and temperature, and is independent of the shape and size of the battery. How to write primary cell? The left is the electrode where the oxidation reactions occur. The right is the electrode where the reduction reactions occur. Single line represents the two-phase interface. Double line represents the salt bridge connections between the two liquid phase interface. The electromotive force of the above-mentioned primary cell can be simplified, expressed as battery electromotive force equal electrode potential of positive electrode minus electrode potential of negative electrode. The interfacial potential difference of a single metal electrode, that is, the magnitude of the metal electrode potential is determined by the charge density of the electric double layer of the metal surface. The properties of the double layer depends first of all on the type and properties of the metal, but is also closely related to the solvent properties, the activity of the metal ion in the electrolyte solution, and the temperature. Next, the properties of the electric double layer will be discussed. When the electrode is in contact with the solution to form a new interface, due to the great difference in the physical-chemical properties of the different phases, the forces on the particles between the two-phase interface are always different from those on the internal particle of each phase. So the rearrangement of free charges or oriented bipolars will occur between the interfaces to form a bilayer, and there is a potential difference in the interface area. Depending on the structural characteristics of the electric double layer in the two-phase interfacial region, it can be classified into the following three types: ionic double layer, dipole double layer, adsorption double layer. The potential difference between the metal solution interface is composed of some of the three types of the potential difference mentioned above. But it is the potential difference of the ionic double layer that has a significant effect on the electrode reaction rate. The first bilayer model was first proposed by Helmholtz in 1879, who devised the bilayer model by considering the rules of positive and negative charge arrangement on both sides of the rigid surface. As shown in the figure 17a, if there are two layers of free charges of opposite sign distributed on each side of the interface between the electrode and solution, there is a certain amount of residual charge in each phase. The Coulomb force acts so that all these residual charges are distributed in the surface interface area, similar to the parallel plate capacitor. One plate in the metal surface is in contact with the solution, and the other plate in a plane needle arranged in the center of the ion of different charge of the metal surface. The charge density is proportional to the interfacial potential difference produced by the bilayer. In concentrated solutions, especially when the potential difference is large, the capacitance value calculated by the Helmholtz model can better match the experimental results. So this model also reflects the real structure of the bilayer under certain conditions, but this model has two main drawbacks. First, it only considers the interaction between the electrode and the adsorbed layer and ignores other effects. And secondly, it does not consider the effect of the concentration of the electrolyte solution. In the early 20th century, Coy and Chapman independently proposed their model of the bilayer. They considered that both the applied potential and the electrolyte solution concentration affect the capacity of the electric double layer. Since the ions are free to move, they devised that the electric double layer are not tightly packed as described by Helmholtz, but have different thickness. This model is called the diffuse electric double layer. In the diffuse electric double layer model, the distribution of particles at different distance from the electrode obey Boltzmann's law. The thickness of the diffusion layer can be expressed by equation 17. From this equation, it can be seen that it is proportional to the root of the temperature, which reflects the relationship between the energy of the ion and the thickness of the diffusion layer. The higher the energy of the ion, the greater the thickness of the diffusion layer. The diffusion bilayer capacitance can be expressed by equation 1H. The variation of capacitance with potential due to the hyperbolic Poisson term is shown in the figure 110. In 1924, Sturm combined the Helmholtz model with the Coy-Chapman model, in which he considered the formation of a double layer immediately adjacent to the electrode as a compact layer, followed by a diffusion layer extending into the solution. Interpreting the experimental results with this model, when moving away from the zero charge potential, the electrode exerts a strong force on the ion, causing the ion to be strongly placed on the electrode surface, and the potential drop during this distance strictly follows the law of the adsorption layer. Near zero charge potential, there is a diffusion distribution of ion. Expressed in a mathematical formula, it is equivalent to the two series capacitors, where C8 represents the compact layer capacity, and CGC represents the dispersion capacity. The smaller of these two capacitance determines the observed properties of the electric double layer. The following two extreme situations satisfy the assumption of the model. In the Goy-Chapman model, the higher the electrolyte concentration, the thinner the dispersion layer, and the faster the decay of the potential. The distance is the interface between the closed layer and the dispersive layer, and this interface is called the outer Helmholtz surface. We'll talk about the formulation of the inner Helmholtz surface later. It can be seen that the Stern model is the best among these three models, but it does not explain all the shapes of the curve. For example, a liquid electrode made of mercury is a special case, and the results for other electrolytes with solid electrode exhibit more complex properties. The Stern model distinguishes between ion adsorbed on the electrode surface and the ion on the diffusion layer. In 1947, Graham proposed the concept of three zones. The difference from the Stern model is that the existence of the characteristic adsorption is considered. The ion adsorbed by the characteristic remove the solvation effect and are in close contact with the electrode surface, and they are not only affected by the electrostatic force, but also by a special adsorption force, which is not Coulomb's gravitational force, and they have the same sign of charge as the electrode, or the opposite, but the binding force is very strong. Figure 1.13 shows the ion distribution and potential distribution of the Graham electric double layer model. The inner Helmholtz plane is the surface at the center of the adsorbed characteristic ion. The diffusion layer is outside the outer Helmholtz plane. In the Stern and Graham models, the potential varies linearly up to the outer Helmholtz plane, and the diffusion layer changes exponentially. And figure 1.14 shows the variation of capacitance with potential for the Graham model, from which it can be observed that the capacitance variation of this model is closer to the actual capacitance variation curve with potential. The characteristics and non-characteristics adsorbed ion are listed below. In 1963, Bockris proposed an electric double layer model that includes a solvent factor. In polar solvents such as water, the concentration of the solvent is almost always higher than the concentration of the solute, so there is always an interaction between the electrode and dipole. The Bockris model takes into account the solvent factor and assumes that the solvent molecules are preferentially arranged on the surface of the electrode. The orientation of the solvent dipole molecules is based on the nature of the charge of the electrode, where the dipole solvent molecules are on the same layer as the characteristic adsorbed ion. The electrode is a giant ion, and the solvent molecular dipole forms the first layer. Inner Helmholtz plane is the interface plane through the center of the solvent molecular dipole and the characteristic adsorbed ion. The outer Helmholtz plane is the plane through the center of the solvated ion adsorbed layer, and outside the outer Helmholtz plane is a diffusion layer. The variation of the potential with distance is shown here. From a qualitative point of view, this figure is identical to the Graham model. Bockris also defines an interface plane. This interface plane allows free movement of the ion except for the ion at the interface plane, which is tightly cropped to the electrode and approximates the outer Helmholtz surface, but does not necessarily perfectly match the outer Helmholtz plane. This is a very important interface plane for the electrical potential. The potential of this surface is called the potential Z, or electric potential. The concept of bilayer is far from perfect, and the model we mentioned earlier mainly considers the role of the electrostatic force. At the solid solution interface, we need to take into account the electron distribution of the atoms in the solid electrode. There is a difference in the electron distribution due to the different work function of different solids. The first solid solution interface region model based on these principles was proposed by Damaskin and Franklin. Subsequently, the models evolved gradually. Transity and Parson have well reviewed the stepwise evolutionary process of these models. A relatively typical of this is the Gerium model. This model extends the interface region to the solid structure. The interfacial potential difference starts from the inside of the solid, which is called the surface potential. With the development of the spectroscopic techniques such as on-site infrared, Raman spectroscopy, and others, which are used to observe surface structures and calculate the bond state of electrode surface, has allowed people to gain a more specific and detailed understanding of various interfaces. Solid electrodes have a fixed structure and can be polycrystalline or single crystal. In metal electrodes, electrons conduct electricity, mainly because valence electrons are free to move. The electrons that pass through the interface are those in the Fermi level, whose energy is related to the electron arrangement of atoms in the metal section lattice. In the case of metals, the occupants of electronic energy levels close to the Fermi level can be calculated and expressed by equation 110. Many factors affect the interfacial structure of a solid electrode, and the distance between atoms depends on the crystal plane and the interfacial energy. There are structural interruption and one- or two-dimensional defects between different crystal and polycrystal materials. For example, there are helical dislocations. Some of them are favorable for adsorption of materials and some are unfavorable for adsorption of materials. From a microscope point of view, what was observed was the nature of the average. The conventional explanation is that all the potential drops are on the side of the solution. Experimentally, this is not true, and Gerium model proves to be more correct. It shows the fact that electrons in solid pass a small distance and more into solution. According to this process model, the internal potential associated with the Fermi rank and the external potential of the electrode electron distribution distinguish the external electric from each other. The difference between the two potentials is the surface potential. The contents of these introductions are squeezed in the summary as follows. This concludes the Introductions to Electrochemistry Basic Knowledge, Part 1, Some Basic Concepts of Electrochemistry. I wish you enjoyed the lectures. If you have any question, please feel free to contact us. The next webinar we are working out to have for the beginning of October. For today, thank you again and stay safe and healthy.